Hello friends and students. In last lecture we have seen what is meant by interhalogen compounds, what are their types and how to prepare them at lab scale in laboratory. Now in this lecture, this will be an extension of that previous lecture, and in this lecture we are going to see the structure and bonding in interhalogen compounds. We will see a structure and bonding for each class, that is for XY, XY3, XY5 and XY7. So one example each time we are going to see, so that you will get a better idea about what is the structure and bonding present in interhalogen compounds. Okay. So first is a diatomic, that is ICl, ClF or IBr, whatever you want. The same structure will be shown by these three compounds. Let's see ClF, that is chlorine monofluoride. Chlorine monofluoride. So in chlorine monofluoride, if we want to see the structure, we want to know what is the hybridization present in the compound. Now in this molecule, chlorine will act as a central atom. This chlorine is a central atom in this molecule, and thus it will undergo hybridization. Now for example, if you see the valence electron configuration of central atom, that is chlorine, it is a 3s2 3p5. It is a 3s2 3p5. Thus, if we see, then this chlorine will undergo sp3 hybridization. Chlorine will go in a sp3 hybridization. How it will show, that will be seen in our next slide. Now for example, as I said, that it will go in sp3 hybridization. In order to know in detail, we have to write its ground state electron configuration and its excited state. So in ground state, it will show 3s2 3p5, and also in excited state it will show the same configuration. This 3s and 3p will undergo hybridization. They will combine and they will come to the same energy level, that is a sp3 hybridization. So these orbitals are called as sp3 hybridized orbitals. So these are called as sp3 hybrid orbitals or sp3 hybridized orbitals. Now if you see, there is one place empty, and in this place this fluorine will share its electrons, and thus this configuration, or this we can say the orbitals will get fulfilled their electrons. Now if you see how many lone pairs will be there, then it is seen that there are three lone pairs. This is number 1, this is number 2, and this is number 3. So these three lone pairs will be present in that molecule, and there will be one bond pair. So this last one is a bond pair present in this molecule. So from the above representation, it is clear that there are 3 lone pairs and 1 bond pair. Thus we know that the sp3 hybridization has a tetrahedral geometry. sp3 hybridized orbitals has a tetrahedral geometry. Having angle of 109.5 degree. This is the angle. This is a normal tetrahedral angle. Okay. Now, as there are 3 lone pairs, so for example, in this example, if you see, so this is a lone pair, this is also a lone pair, and this is also a lone pair. So there are 3 lone pairs and only 1 bond pair. This is a bond pair and this is a CL. Thus, the structure, the shape of this molecule will be a linear. It is a linear molecule. Right? And thus, the angle between this fluorine and chlorine, of course, is a 180 because this is only a diatomic molecule. So there is no question about that bond angle between fluorine and chlorine. It must be a 180. It is 180 indeed. Although these lone pairs can repel each other, there can be a repulsion. But anyway, the repulsion will not result in any distortion because there are only 2 atoms, chlorine and fluorine. So there is no change in the bond angle. The bond angle will be a 180. So there is no, this is very straightforward. Now in another example, we are going to see the structure and bonding in tetra-atomic interhalogen compound. And the example we will see is a chlorine trifluoride. The example we will see is a chlorine trifluoride. Similar structure can be explained with the help of this valence bond theory and VSEPR theory, valence shell electron pair repulsion theory. For bromine trifluoride, for iodine trifluoride, and for iodine trichloride, the same structure will be there. Only some bond angles will be changed, but the overall structure will be same. That is a bent T shape. That we are going to see why this molecule shows a bent T shape. Okay, so again this structure will be explained on the basis of hybridization. In chlorine trifluoride, the central atom is of course chlorine. Why central atom is chlorine? Why not fluorine? Because chlorine has a bigger size than the fluorine, so it will act as a central atom. And also chlorine has a less electronegativity than the fluorine. Understood? Now we have seen the valence shell electronic configuration of this chlorine is a 3s2 3p5. Now in order to accommodate 3 fluorine atoms, this molecule has to undergo sp3d hybridization. Resulting trigonal bipyramidal geometry. The geometry will be a trigonal bipyramidal, but the shape will be different. And this we are going to see in this slide. Now in this slide we have seen we can see that in ground state configuration, if you see, this is the ground state electronic configuration, that is 3s2 3p5. Now in first excited state we can say the 1 electron from 3p will migrate to the 3d. 1 electron from 3p will migrate to the 3d, and thus you will get these orbitals like sp3d or hybrid orbitals. So it will be So they have already shown this sp3d. So you can see these three orbitals. So this is a s, this is these three orbitals are p, and this is a d orbital, right? So s, 1s, 3p and 1d. So it is a sp3d hybrid orbitals, sp3d hybrid orbitals. And generally we see the geometry of sp3d hybrid orbitals is a trigonal bipyramidal. So for example, this is a trigonal, and bipyramidal. So two fluorine will be on the axial position of this pyramid, and one fluorine will be at a equatorial. So this is equatorial position in the pyramid. This is a pyramid. This is a trigonal pyramid. If you see these 1, 2 and behind it is a third face of this pyramid. So it is called as a trigonal because there are three angles, 1, 2 and 3, trigonal, and bipyramidal because there is one, this is a one pyramid and there will be another at the bottom. So this is called as a trigonal bipyramidal. This position is called as a axial position. This position is called as a axial position. This position is also called as a axial position. Okay, so this is why it is a trigonal bipyramidal, but the actual shape will be only determined by this number of bonds. So there are only three bonds. This is one bond, this is another bond, and this is another bond. So the shape of the molecule will be simply a T shape, but it is not exactly T shape because these angles are not exactly 90 and 120, but these are somewhat less than that. This is because there is a repulsion between these non-bonded electrons. So these lone pairs will repel each other, and this will also repel with each other. This bond pair, this lone pair, and this is a bond pair. So these are bond pair electrons. So there will be electrons, 2 electrons here, and there will also 2 electrons here. So these 2 electrons are called as a bonding electrons because these are involved in bond between chlorine and fluorine. So these are called as a bonding electrons, and there will be, these are lone pair electrons because there is no bond, right? So that's why this is called as a lone pair of electrons or non-bonding electrons. Now there will be a repulsion between this lone pair electrons and this bond pair electrons. So because of that, these fluorines will try to go away from this lone pairs, or they will try to go towards this fluorine. So it will be like a bent T-type, bent T-shape. Thus remember, these tetra-atomic interhalogen compounds generally shows bent T-shape. Their geometry is trigonal bipyramidal, but their shape is bent T-shape. Right? So according to VSEPR theory, shape of ClF3, that is chlorine trifluoride, is bent T-shape as it contains 3 bond pairs and 2 lone pairs. So these are 3 bond pairs. This is 1, this is 2, and this is a third one. Okay, and these two are 1, or we can say A, and this is the B. These A and B are lone pair of electrons. So these repel these fluorine atoms towards this fluorine atom, and that's why it becomes a bent T shape. Okay. Out of 5 hybridized orbitals, 3 contain bond pair and 2 contains lone pair. So from this also we can say, so this is lone pair, this is a lone pair, these three are bond pairs. These three are bond pairs. So in this way we can explain the structure of this uh, interhalogen compounds containing 4 atoms, that is a tetra-atomic interhalogen compounds. In next slide we will see structure and bonding in hexatomic interhalogen compound, that is AX5 type, that is a AX5 type. Now in AX5 type the examples are iodine pentafluoride. The examples are iodine pentafluoride, or there is another possibility, bromine pentafluoride. Although this bromine pentafluoride is little bit less stable than the iodine pentafluoride. Iodine pentafluoride is a quite a good stability than the bromine pentafluoride. Okay. Now in iodine pentafluoride, central atom is iodine, and it has a valential electron configuration, that is a 5s2 5p5. Its outermost electronic configuration, or we can say valential electronic configuration, is 5s2 5p5. In iodine pentafluoride, central atom, this is wrong, iodine, it should be iodine, sorry, this is wrong. The central atom iodine undergoes sp3d2 hybridization. The central atom iodine undergoes sp3d2 hybridization, resulting octahedral geometry. Resulting octahedral geometry. According to VSE pair theory, shape of IF5 is a square pyramidal due to 5 bond pairs and 1 lone pair. And also the bond angle is 81.9. Instead of bond angle of 90, it shows 81.9. So it decreases, and this decrease in bond angle is due to the bond pair and lone pair repulsion. Bond pair, lone pair repulsion. That we are going to see in next slide. So here what happens? We have this 5s and we have this 5p and this 5d. Now in order to accommodate 5 fluorine atoms, these 2 electrons, this is one and this is another 2. So these 2 electrons has to move into the 5d orbitals. So in excited state what happens? These 2 electrons, one from this orbital and another from this orbital, migrate or excited into a d orbital. So there is a set of almost 6 orbitals, that is s, 1s, then 3 p's and 2 d's orbitals combined together to form a hybrid sp3d2 orbitals. Hybrid sp3d2 orbitals. Now the shape of molecule is mostly uh, driven by this number of lone pairs. Now in this molecule there is only one lone pair. This is the one lone pair, and these 5 are bond pairs. These all 5 are bond pairs, and in each orbital there will be one electron shared by this fluorine atom. So these 5 fluorine atoms will share one electron each with this 5 chlorine orbitals in order to fulfill their duplet. Okay. Now because of this lone pair, there will be a repulsion between this
lone pair and this bond pairs. So bond pairs, there are electrons. These are bond pair electrons or bonding electrons. So because of same charge, the lone pair has electrons and bond pair are also electrons. So there is a repulsion between like charges, same charges, and that's why it will try to repel this bond pair, and that's why this fluorine, these all fluorines, these all four fluorines will try to move away from this lone pair and towards this fluorine atom, and thus this angle becomes 81.9 instead of a 90 degree. Instead of 90 degree, it shows a 81.9 degree angle. Okay, and also if you see the angle between this axial fluorine and iodine, the distance between this axial fluorine and iodine is 184.4 picometer, while the distance between this equatorial fluorines in the square planar, in the square plane, this is a square plane, is a little bit higher. So even this bond length also we can say influenced due to this lone pair. This bond length is also influenced because of this lone pair. Okay, understood why this angle is less than 90? It is because this lone pair repels this bond pairs, and because of that this fluorine atoms try to go away from this lone pair, and thus this angle becomes less than 90. So this angle decreases from 90 to 81.9 degree. Okay, now next molecule, this will be a last molecule in this series, is a iodine heptafluoride. Iodine heptafluoride. This molecule is octa-atomic molecule. This molecule is a octa-atomic. Octa means 8 atomic. The 7 x's and a, so ax 7 type, or we can say xy 7, or we can say xy 7 type. We can say xy 7 type molecule. Okay, and also in the similar manner the structure and bonding can be explained on the basis of hybridization. In IF7, central atom iodine has a valence shell electron configuration same 5s to 5p, 5s to 5p 5, 5s to 5p 5. Okay, in IF7, central atom iodine undergoes sp3d3 hybridization. sp3d3 hybridization. Now sp3d3, why? Because there are 7 fluorine atoms, so all 7 fluorine atom has to be accommodated inside the orbitals of this iodine, and for that it has only 7 orbitals possible, 7 electrons, 2 electrons from S and 5 electrons from P, so these are 7 electrons. So all 7 orbitals or all 7 electrons will try to get together to form sp3d3 hybridization. Okay, so hybridization resulting in pentagonal bipyramidal geometry. It has a pentagonal bipyramidal geometry, and it has a shape also same. So shape will be also same, that is a pentagonal bipyramidal, because there is no lone pair possible. There is no lone pair in this compound, that's why the shape will be a regular pentagonal bipyramidal. Regular pentagonal bipyramidal. According to VSE pair theory, lone pair is 0. Therefore, IF7 has a regular shape. In IF7, all 7 hybridized orbitals form 7 covalent bonds. How many covalent bonds will be there? 7 covalent bonds with fluorine atom having a regular shape. With a fluorine atom it will form a 7 covalent bond. This iodine will form a 7 covalent bonds with the fluorine, 7 fluorines, and that's why it has a regular shape. That's why it has a regular shape. If you try to understand how this shows a 7 bonds, then we have to check its electronic configuration first. So let's see electronic configuration. So for example, iodine has a s5s2 5 orbitals. So it is a ground state orbitals 5s2 5. Now these 3 electrons will migrate. These 3 electrons will migrate to 5d orbitals. So this one from 5s and then 2 from 5p electrons will migrate to the 5d orbitals, and it will form a 7 hybrid orbitals, that is a sp3d3 hybrid orbitals. In each orbital there will be a fluorine. So these all 7 electrons are shared by these 7 fluorines, okay, and thus it will show a pentagonal bipyramidal shape. So this is a pentagon, this is a pentagon, this is a pentagon, and this is a pyramid's axis or axial positions of the pyramid. Now these angles are 90, that is a very much normal angle, and this angle between two fluorine in the pentagon is 72, that is also very much normal. The only thing is that the axial bonds, that is IF bond, is little bit shorter than the equatorial bond. This is only a difference, otherwise it is very much a regular pentagonal bipyramidal, very much regular pentagonal bipyramidal. The only thing that there is a little bit difference between axial bond length is smaller than equatorial, and this is a valid in most of the compounds. So most of the compounds which are pentagonal bipyramidal, their axial bond length will be shorter than their equatorial bond length. In trigonal bipyramidal shape also, the axial will be shorter than the equatorial in other molecules also. Okay, so this was all about the bonds or shapes of the interhalogen compound, that is geometry and shapes of the interhalogen compounds. Now if you have any doubt, then please comment below. I will see them and I will tackle your problems. I will try to answer with my best. I will study more. If you want more videos on these topics and many other topics from the chemistry, then please let me know below in the comment section. Okay, so we will stop here. Let's meet in new video or new lecture. Until then, goodbye and good luck. Thank you.